Let's get started. I've got one last question I wanted to do from the intro to random variables, and then we'll get started on our last section for this week, and also the last thing you need to know for your midterm. So being the last question, it's kind of convoluted, so here goes. There's a story. A woman decides to have children, and she decides she's going to do it until she gets her girl, and then she'll stop, or until she has 4 children, which is exactly what my sister Morag did. She wanted a girl, and she kept on getting boys. And when she got to the 4th boy, she just gave up. It's kind of the quirks of probability. Every one of her sons, when they had families, every single one of them, the first person that was born was a girl. So she ended up with lots of grandchildren, girls. She just couldn't get one for herself. So this woman here is very like my sister's kind of situation. And so they tell you the sample space, but they don't need to. In this case, the sample space is she gets a girl. That's the end of the line, right? Or boy first, and then she gets a girl. She stops. 2 boys, and then she gets a girl. She stops. 3 boys, and she gets a girl and stops. And then 4 boys in a row, and that's it. 4 kids. I'm having no more. The sample space is a list of all the things that could happen. So in this story, that's all the things that could happen. So let's see what the probabilities are. Well, we're assuming that they're independent. In other words, if you get a boy before, the chances you get a boy or girl next is still 0.5. So probability of a girl, 0.5. The probability you get a boy and then a girl is 0.5 times 0.5. We're using the formula or the property that if 2 things are happening and they're independent, you can multiply them together and you get that. Now this one would be a boy, 0.5, times another boy, 0.5, times a girl, 0.5, and this ends up being 0.125. And then you get this one, which is basically going to be 0.5s all the way, including the last one, which is a girl. And that's 0.0625. And this one essentially ends up being the same multiplication. And this one ends up 0.0625. So you've been asked to calculate the probabilities, and all you do is you multiply each event together. Right. So just reflect on this one again. A boy times a girl. Probability of boy times probability of girl. This is your answer. And then they've got a little probability distribution here, where K is the number of children she ended up in her family. Right. She could have 1 person in her family, and that's because she got a girl. And that's 0.5. She could have 2 kids in her family, and that happens with a probability of 0.25. 3 kids in her family has a probability of 0.125. And 4 children in her family is actually made up of 2 distinct events. And both of those situations where she would get 4 children. This one was 3 boys and a girl, and this is 4 boys. So you would add these 2 together and get 0.125. If you do a probability distribution table, as we've just done, what should the total add up to if everything was done correctly? That's it. Should be 1. You can check this, it is 1. So do you see that if you set up the story carefully enough and create a sample space, couldn't you find a probability distribution for almost any combination of events you're interested in? It's all about sample space, independence, multiplication to get individual pieces, or in this case, still multiplying, but adding 2 together because they count as in this case, 4 in a family, right? Are we good? Right. And that is the end of that. So we are now moving on to the second part of chapter 8. And this is going to be what's called the normal distribution. And we have touched on some of the topics that they return to here, right? So in a lot of cases, you collect information and you find out that the population has a shape like that. And we have a normal, well, we've quite a few names for these. This shape here is called a bell-shaped. It's one of its names. It's also called a normal distribution. Does anybody know the third name? And we have used it. What would you call a distribution that looks like that?
Symmetrical.
Yeah. So in this case, we're looking at bell-shaped. I'm going to stop for a second. My little dog is making a noise that is not a good sign. And she finds cables everywhere. What's she doing? You little bugger, come here. Chloe, come. You know what the little bugger was doing? She was chewing on the wood of her, do you know the thing, I don't know what you call it, you know the wood that goes along the bottom here, between the floor and the ground? The strip of wood, that thing. She was chewing on it, the little darling. Okay, focus. Right, so bell-shaped, normal, and symmetric. Very common shape, very useful. We actually hope to find that shape in data because it allows us to do a lot of probabilities that would be impossible otherwise. Another thing that we have mentioned is a thing called the Z-score, or its full title is the standardized Z-score. And it had a formula that looked something like this. The data, take away the mean, divided by standard deviation. If you want to write it with a little bit less words, data, take away the mean, because that symbol means the mean, and SD for standard deviation. Remember that guy? Standardized Z-score, it's how we could tell, how we could compare two groups. You know, the one like Mary got this in the exam and John got that. We used it for that. And we're going to use Z-scores again as well for some of the questions. So this is not new, right? Maybe just a new name, normal distribution. If data has this nice shape to it, or at least approximately that shape, because we know in real life nothing's perfect, we'll call it a normal distribution. And when you have normal distributions, you can calculate Z-scores, provided someone tells you the mean and standard deviation. So it's just a recap of things. Now, X bar is the mean of a sample. And SD is the standard deviation of a sample. This is the Greek letter, which you pronounce as mu. And this is a Greek letter, you pronounce it as sigma. What does mu tell you? What is mu? Okay then, to remind you, it's the mean of the population. And sigma, I'll have to do SD, it's the standard deviation of the population. When you get a number, like a mean or a standard deviation, but that number was found by using a sample, it's called a statistic. And when that number, in this case mu or sigma, is found by doing a census and asking everybody, right? So you get it from the population, and this is called a parameter. Okay, so we're just going over some of the terminology that's is going to get mentioned from time to time. Pretty sure you remember that one. I hope I mentioned this at least once. I'll mention it again if I haven't. Statistic, parameter, sample, census. Some people, all of the people. Right? So we're going to bring together this, this, and this. So the first couple of questions are all about finding a z-score, and we're going to be using this version of the z-score. Data, take away mu for sigma. In other words, the numbers for the mean and the numbers from the standard deviation come from a population. So this is an example of question 1B. And we're being asked to calculate the z-score when the mean is 12 and the standard deviation is 4, and the data, which they are just going to call x, is equal to 10. So the z-score is going to be the data, take away the mean, divided by the standard deviation. You can do that in your calculator and you get negative 0.5. Are we okay with that kind of calculation? If you tell me the mean, the standard deviation, and what the data is, they're just going to call the mean mu. The standard deviation of the population is going to be called 4. And instead of saying the word data, they're going to just call it X. Is that good? Any problems with that? Okay, let's look at another one. This is from question 2C. In this case, mu is 77, so the population mean is 77. The population standard deviation is 8, and the data is 95. So the z-score in this particular case then is 95, take away 77, divide by 8. That's 18 divided by 8, which is 2.25. Right. Suppose I have two z-scores. One of them was 1.9 and the other is 3.9. So suppose I had some data and the z-score of my first set of data was 1.9 and the z-score from my second piece of data was 3.9. Which one of those two is an outlier? The one that ended up being a z-score of 3.9 or the one that ended up having a z-score of 1.9? Which is the outlier?
3.9.
And we have a little test for that, don't we? And the test says you are an outlier if your z-score is bigger than 3, right? Now here's a little bit different question, and it's not to do with outliers, but it's to do with z-scores, and it's one of the reasons we would calculate z-scores. So neither of these are outliers, right? The data that generated this z-score and the data that generated that z-score are not outliers, right? Oh, the other way, isn't it? You're an outlier if the z-score is like -4 as well, right? That would mean it's a small outlier. Right, back to this question. Which one of these two events is less likely? And all you know is its z-score.
-2.1.
Correct. What made you come to that conclusion?
Because it's further away from 0 than 1.9.
Yeah, that's a good way of phrasing it. So let's give you a little story that might be attached to that. Suppose we live in a place where the mean temperature, right, in, let's do summer. The mean temperature in summer is 80, and that the standard deviation is 4 degrees. And in the winter, the mean temperature is 50, and the standard deviation is, say, 5. And there's a temperature in one day that happens to be 75 degrees. So the question is it more or less likely to get 75 degrees in the summer or in the winter? Now, if you were just looking at it, you'd say, well, it's getting 75 in the summer. Well, the average is 80, so 75, wouldn't that just be a kind of slightly cold day in the summer? Not freezing cold, just slightly cold. Now, the winter temperature is 50. Couldn't 75 just be an extra special warm day in winter? But the question was, which is the most likely, right? Getting a temperature of 75 in the summer or getting it in the winter? And the way you could answer that question is you find the z-score. And whichever one of them is the smaller is the most likely, and whatever one of them is the biggest is the less likely. Depends how the question is phrased. So if I do this, I'll do this in green, I think. If I do the z-score here, it's going to be 75, take away 80, divided by 4, and I believe that is -1.25. And if I do it for here, it's going to be 75 take away 50 divided by 5, and that ends up being 5. And so kind of our gut feeling was right. Would it not be more likely to be a temperature in the summer than one in the winter? Right. It's a little bit cold in the summer, but it's certainly doable. Would it not be an exception, an outlier in the winter? So you can answer questions like that as well using z-scores. So they're quite flexible. And I'm just scanning through. That's kind of the stuff that we've seen somewhere in different forms. Now we're going to do some new stuff, and we're going to have to use salt. So we're going to look at a special version of the normal distribution. The standard normal distribution comes from z-scores. So can you imagine you collected a whole load of data and you turned all of those data into their z-scores, you would get this shape. And the mean right in there. What should the mean be for all the z-scores? It's one particular number and it's always the same number. What's the mean of all the z-scores of some data? What's the number that you would expect to be bang in the middle for a z-score?
0.
It's 0. Can you imagine how that would come about? Wouldn't that be when this was 0? Wouldn't this be when you got the mean? That makes sense. Now, it's less likely or less obvious, but the standard deviation is 1. And so if you create, and hopefully you remember this picture, can you remember the 1, 2, 3 standard deviation thing? We can use SALT now to find probabilities like this. What's the probability that you get a z-score greater than or equal to any number you like? I'm just picking one at random, 1.35. Now, we used this guy, but didn't we use it in a quite crude way? From 1 to -1, isn't that one standard deviation? So that was 68, then 95, and then 99.7. That was as good as we could get. But we can now use SALT to actually find the probability that you get any z-score. So how likely is it to get a z-score bigger than this, right? Or how unlikely if it's a small number? Now, if you want to visualize where that would be, it'd be roughly about here. And you're trying to calculate that bit. Because technically, the shape of this curve has a really interesting property. Its entire area is 1. So if you find that area, it's equivalent to the probability. It's just the way the math works. And we are going to find that probability. But we're going to let SALT do all the hard work for us. So I'm going to take you through that now. And hopefully it'll work. Right. You should be looking at question 3 here, are you? Right. And there's that big orange SALT button. And the one that you want, I'm going to shrink this up, it's a bit too big to see what I need. Right, the one that you want is distribution calculations. Do you see that? And there's lots of different ones, but you want the one called normal distribution. And in this case, it's a z-score, so the mean is 0 and the standard deviation is 1. So if that's not the numbers you're looking at, that's what you should make them into. And then you have a little left tail, right tail, both tails, or between story, right? Now, the one we wanted was bigger than. Can you see it looks like my little picture that I had a minute ago? So if you want to know a z-score bigger than somebody, you use a right tail. If you want to find the probability that you get a z-score less than something, you use the left tail. If you wanted to know the chances of getting a z-score between two things, you would use the between one, right? Now we wanted a right tail. Now you go over here, it's kind of faint, but I can see it. You put the number that you were looking at, in this case, 1.35, and the probability is that, and that guy has a probability of what, 0.08851. You agree it's reasonably easy to use SALT to do those kind of questions? Make sure it says normal, make sure when it's a z-score that it's 0 and 1. Pick whichever one of these is the appropriate one for the question. In this case, that one. Put in the number you need, And right underneath that little decimal is the probability that you are looking for. So if you kind of forget how to do this, this piece of the video would probably be the place you'd go back, hopefully, and look at it. So that is how you can find how likely or unlikely it is to get a particular Z-score. So I'm going to build just a little list of questions. What's the probability that we get a Z-score greater than or equal to 3.1? Wouldn't that be an outlier if you get a Z-score that was that kind of number? So let's see how unlikely that one is. My second question is, what's the probability that you get a Z-score less than or equal to 1.2? Let's find the probability that you get a Z-score less than or equal to negative 0.123, just to be awkward. And let's do a between. What's the probability that you get a Z-score between 2 and negative 2? Isn't that 2 standard deviations away from the mean? Right, this one here. 2 standard deviations away from the mean. What is that number? We already know it from the empirical rule. What percentage of the data is 2 standard deviations away from the mean, approximately? 1 is 68. How much is 2? In fact, it's got a weird name that tells you the answer, isn't it? 68, something, 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 right? 68, what's the next one up?
95.
Okay, correct. And isn't the one after that 99.7? Wouldn't that be a useful thing to know in a midterm exam without you having to look through 12 pieces of paper to find the one where you wrote it down? Some things are just better memorized. They're just less work and everything. Right, so I kind of know that answer, which I guess is going to be about 0.95. I wonder how good salt is going to be at doing that same thing. So I'm returning back to here. Right, Z greater than or equal to 3.1. Well, this one's already set up. 3.1, getting a Z score of that is, oops, that's weird. 3.1. And look at the answer. Its chances of happening, of getting a Z score that size or bigger, is 0.009. If I round it off, it's 0.01, or about 0.1% of the time. Would you agree that's why it's an outlier, right? It's a very unlikely big score. Now, the next one I had was less than 1.2. So if you want a Z score less than, you click that guy. And then over here, you put in 1.2. And the answer we got this time, and I'm just rounding them off, is about 88%. So 0.88, about 88%. And the third one I have is less than negative 0.123. So it's a left tail. And it's less than a Z score, so negative 0.123. And the answer you get is about 45%. And now the between one. Between. On this side, greater than 2. And on the other side, less than negative 2. That seems to me a bit back to front. Wouldn't you switch places with them? It would look more natural, but that's how you do it, greater than 2 and less than negative 2. So what's the problem? Oh, that's the right way around. Okay, it was telling me I screwed up. And the answer is, would you agree that's darn close to 95% if you round it off? So if you wondered, where did the 95% come from? It came from a program like SALT and experience. Are you comfortable about how you can use SALT to find any of these types of probabilities? That's pretty powerful, isn't it? That we can now collect data and then tell people how likely a particular number in that data is likely to be. Pretty powerful. And that's basically questions 3 and 4. Checking it out. Also 5. So where are we off to now? Well, imagine that we just collected a normal distribution. And it was to do with IQs. And the mean is 100 and the standard deviation is 10. And that I know when I looked at the data that I had, and I looked at all the IQs of people, that it was normally shaped, right? So it would look like 110, 120, 130, 90, 80, 70, right? You can be asked very similar questions and SALT will get the answer. You can ask, for instance, what's the probability that you pick someone in the population at random? And when it's a Z-score, we call these numbers Zs, but when it's any other data, we just call it X. So what's the probability that you get someone's IQ and it's greater than 110? Or what's the probability that you pick someone and their IQ is less than or equal to 81? Or you get to, oops, let's see, what's the probability that someone in the population has an IQ between 81 and 112? So these are the 3 guys. Now SALT will do that as well. Before we go to SALT, let's talk a little bit about how we're going to set this up. Is this going to be right-tailed, left-tailed, or a between? What one will I use on this first question? Right-tailed, left-tailed, or a between?
Isn't it right-tailed?
Correct. And this one would be left. And this one would be a between. Would you agree the between one is the easiest to recognize? Anybody got a short, quick way to remember which one of these is the right one?
To look at the sign in between, usually, isn't it?
Yeah. The way I do it is I think of that as pointing right, and I think of that as pointing left, and that kind of helps me. Can you see? Pointing right, pointing left. It's easy. And I think, as I said, between are pretty obvious. So average IQ is 100, standard deviation of the population is 10. We can look at this and we can find out what percentage of the people have an IQ greater than 110. So let's show you how SALT does that as well. I don't think I hit the wrong button there. Let me try it again. Maybe I do. Are you looking at the normal distribution guy? Right. Now we have to do some changes here. That's still normal, but actually SALT is quite versatile. We can put in any mean and any standard deviation. Do you see that? So you put in 100 for the mean, you put in 10 for the standard deviation, and then you just do what you would have done anyway. So an IQ greater than 110 is a right tail. And you go over here and you put in 110, and the answer you get is about 16% if you round it off. Now, what kind of people have an IQ that are less, what percentage of people have an IQ less than 81? A left tail for less than. Well, there's another way to remember. Less than is left-tailed, L and L. And less than in our question, it was going to be less than 81. And that comes out about 3% roughly, if you round it off to 2 decimal places, 0.03. And the between one, which is called between, it's got to be bigger than 81, and it's got to be less than 112. And that's about 86% of the population. So if you randomly pick someone and they knew what their IQ was, or they went and got a test after you asked them, 85% of the population has an IQ somewhere in the range 81 to 112. And I got all of that results and any other one I want by simply realizing that the shape was normal and that salt could do the rest of the calculations for us. So if you collect a decent sample size, don't you pretty much know everything about that population, provided that the data has this nice shape to it? That's pretty impressive. Just curious, has anybody ever had an IQ test? Either online as fun or somebody gave it to you at school? Nobody? They kind of died out. I mean, whatever it was, 30 years ago, they were really popular. In fact, some places like universities would give you an IQ test as a way of like an admissions thing, right? You had to get an IQ above this number or you couldn't go to our university, right? Just like, you know, an SAT is not an IQ test, but an SAT score would be very similar. Don't they have universities that say you need an SAT score in math of this number or better, or you can get into the engineering department or whatever it might be? So they used it a lot like that. It went out of favor, quite rightly. If you are interested in IQs, so I'll tell you a little bit about it, is IQs are not measuring how intelligent you are, even although the name is intelligence quotient. It was never really designed to measure how intelligent you are. It wasn't even meant to measure what you know. Right? I know a lot of stuff, or I hardly know anything. It was actually measured, or it was used to measure how easy it is for you to learn something. So it's how quick your brain could pick up a concept it's never seen before, right? That's what it was originally designed for. And if you think of people who are successful, their IQ score is all over the place. There are heads of CEOs and all that kind of in big companies whose IQ is just as normal or even less than some people. And there are some people whose IQs are phenomenally big and are on the streets of Seattle today, right? They just can't function in the world, unfortunately. So examples. Do you know some people who are really intelligent and bone lazy? They just don't study, they don't do anything. They play video games 12 hours a day if you'd let them, right? That person would have an extremely high IQ, but would be functionally not very helpful in a society unless the job was to play video games. The most successful students I've ever met have not been the most intelligent, although there have been exceptions to that rule. The most successful have been the ones who had the right motivation. Right? If you find things are hard, right? If you take English and you had to study hard at it and you had to look up stuff and you had to figure it out and then you finally thought it through and the light bulb went on and you understood it. If that was kind of your college career, if that's how you did things. When you go to university, that's exactly how you're going to be. You're going to get a class and you're going to have to study at night. You're going to have to figure things out, get frustrated, but you've done it before. You know you can do it again, and you fight your way through, and the light bulb goes on, and you understand it, and you're good to go. Very intelligent people very often don't have that skill set of knuckling down and doing it. Fortunately, what happens is that they can breeze through a lot of their classes, right? The night before, they can spend half an hour looking it over, and boom, they know what they need to know, and they know they're going to pass, so they're not worried about it. They hit university, and they eventually, it happens to everybody. No matter how intelligent you are, aren't you eventually going to meet something that's hard and you don't know what it is and you can't make sense of it? Eventually, that hits everybody. Problem is, when it hits those students, they don't know what to do. They've never had to deal with, I don't know how to do something. I don't understand something. They don't have that skill set. And unfortunately, a lot of them just say, well, I didn't want to know that, and they drop out because they don't know what else to do. So, drifted as I do, but that is it. So let's continue with our examples. Oh, before, are we comfortable that you can use the salt to do these probabilities as well? So the questions that did that were question 6, question 7, question 8. Question 9 is actually just like that. The only difference is you're not going to get the thing given to you. They're not just going to say, find this. They're going to be a story, right? So an example of question 9 was, suppose the amount a student at college spends on textbooks, the mean number is $420, right, in a semester. And that the standard deviation is $140, right? So some students spend a lot more than 420, right? Some spend a lot less. Doesn't depend on the class you take. Have you taken a class where the textbook was like $300 and you went, what the heck was going on there? And then you get another class and it's like $20 and you're good to go. But on average, 420, and the standard deviation, it's a big number because there are a lot of variation, is that. So the question they ask is, what's the chance that you get a randomly selected student, right, and they spend more than $500? Well, that becomes X greater than 500. You see, it's just, they don't tell you with X's, they just tell you in English. Well, once you know essentially what you're being asked to find, you can then go to salt, which is what I'm trying to do right now. Here we go. And I'm doing this without showing it. So is that going to be a right-tailed, left-tailed? What's that going to be? The one I've written down here.
Right-tailed.
Okay. You can't see it, but I'm typing in 420 for the mean. I'm typing in for the standard deviation 140. And it's to be a right-tailed, meaning greater than, and $500, just what I'm typing in right now. And the answer that we get here is 0.28, roughly. So there's a 28% chance. You could phrase it another way. 28% of students will spend more than $500 on their textbook this semester. Right? It's just another way of phrasing that same information. Okay. Now, what is, we don't have time for it. Okay. Tomorrow, we will be finishing this section off, and any time we've got left, we'll talk a little bit more about the test. But I want to talk about the test right now, so I can show you some stuff. So while I'm getting myself organized, say your last name for attendance. And right, you should be looking at our Canvas page. Is that right? Okay, so there is a new module, midterm exam information. And if I click on this guy, there we go. Make it that one, make it a little bit bigger. You know it's going to be on Monday, this coming Monday. It's going to cover everything up to and including tomorrow's stuff, which is the section we're on today. We're just finishing it off. It's going to be in two parts. Part one will be in WebAssign. Part one, the WebAssign half of your midterm, is there because don't you have to use salt buttons to do certain questions, like today, for instance, right? So the questions that you would need to use salt will be here, right? In that section one. But they're also going to be a part two, and you'll find that in Canvas. And part two will have, you know, those questions like the probability trees and questions like, what's the probability that you pick a king or an ace? You know, those kind of questions. Questions like, here is a written description, which one of the four is correct? You know, one of those multiple choice kind of vocabulary ones. Very like actually the test that we just did. You know, the online test 4 was full of stories and you picked questions and filled things in. That's where that would go. Now, there are 2 time slots because it depends on your schedule and the exam's going to last 2 hours in total. So 7 till 9, you have to do both parts of the test, or 8 to 10. Right. So if you can get in an hour early, you'll finish at the same time we do right now, or 8 till 10. I do not need to see any working for part one. Part one is on salt, right? Salt, you just do it and it tells you the answers. And part two, I want to see working. So if it's a probability tree, you know, one of those little probability trees, you should be drawing one, right? If it's a probability that you get an ace or a red card, shouldn't you at least tell me the numbers you're going to add and subtract to get the answer that you got? So you show me the working in that. That way I can give you partial credit. That's a biggie. Trust me, you want partial credit. So you want to show me all the working you can. When you're finished part two, so I would probably do the part one you would do in WebAssign, then jump over to Canvas and do part two. That has to be uploaded and I have to see your working. Down here is the Zoom link that you're going to use because you're going to have your camera on all the time during the midterm. Right, I got you, see you, make sure nobody's cheating, keep it fair. Right, so I said that you need to upload your work in this word. To do that, you can use this program called Microsoft Lens if you want, or any other program that you've got. Microsoft Lens can work on your phone. It basically, you take a picture of your work and it converts it into a PDF and stores it so you can upload it. If you've got an Apple, there's the same one. Here's a video that you can watch that kind of takes you through how to use it. So you can use Microsoft Lens, or you can use any software, maybe your English class, use Cam Scanner or something. You can even, if you have, and because you don't want to do the other two, your scanner on your printer. But I need to see it. And once it's done it, you'll put it in a thing like this. Where is it? Oh, I don't have it. Okay. There's going to be a thing that says, oh, I do have it. It's just I couldn't see it. And this is a practice one. Practice uploading your working here. So if you've never done it before and you want to get a shot and make sure you know how to do it, hit this thing. I'll have to put it in student view, show you how it works. You've taken pictures, you've saved it on your phone, put it in, save it on your download part of your phone, wherever you save it. When you come in here, you click it, you say start assignment. If it's in your OneDrive, you click on that. If you use a file upload, choose file. Well, you don't want my tax forms, do you? So pick the one that you want and open it. And then hit submit. And that's it done. If you have a OneDrive, that's kind of helpful because you can say, I think, at least I know how to do it. And can't you save your pictures onto your OneDrive if you want to? And that way, when you go in here, it's waiting for you. Does OC provide a OneDrive account for OC students, or is you have to have your own from scratch? Does anyone know?
You should have your own.
Say it a bit louder, please.
The school should give you one as well as you can also have your own. So it really doesn't matter which one you choose.
Right, so that would, if I was doing, I would probably use the OneDrive, but you know, you can use the other one. Didn't I just click on it and it takes me in, you know, as long as you know where you've stored it, you'll be able to get it, right? So you should be able to do it on your phone. And that is us. Any questions before you say bye-bye? Okay, goodbye from today. Tomorrow we'll finish this off, and whatever time we've got left, we'll do some review for your midterm. See you guys.